thing we have to recognize is just some basic things regarding physics foundation. And so we need to be able to recognize the difference between a vector and a scalar. So vectors have both magnitude or size and a direction. So example of that would be displacement, velocity, momentum. Now scalars are quantities that only have magnitude, and so that's stuff you don't have to specify direction for, like speed, energy, distance. So now when you're adding these vectors, there may be some problems that show up in terms of testing your knowledge on adding vectors. You need to add vectors from head to tail and also include the direction. And the more important part of vectors in terms of the actual exam is being able to break them apart into components. So once you break them apart into components, you want to use the Pythagorean theorem to analyze it. So here's an example. Let's say we had a ball that was launched with 20 meters per second of initial velocity. Because the force of gravity is acting upon the y direction but not the x direction, it affects it differently. So in order to analyze its motion, what you need to do is break it apart into its components. You know the angle measure presumably, and then you can just use trig to find the different velocities, just like that. All right, so now let's get into some of the actual motion stuff for kinematics. So the first thing is distance, which is represented by d, but sometimes it can just be written as d for displacement, like this. So sometimes you can write displacement like that, with like that. But more traditional way to represent displacement is just d with an arrow over it to show direction. So distance is scalar, while displacement is a vector, and that represents change in position, right? So that is otherwise known as final position versus minus initial position. So an easy way to think about that is, let's say you had a guy and he walked forward 10 steps and then walked backwards 5 steps. His total distance traveled would be 15 steps, but his displacement, which is change in position, would be 5 steps. Speed is distance over time. Velocity is change in position over time, or displacement over time. Acceleration is just how fast your velocity is changing over time. And there are the different units, which are represented as meters per second for velocity and meters per second squared for acceleration. Motion graphs, you need to know how to interpret these graphs, and I just have one example here where you can see the position is exponentially increasing, right? So in contrast to that, you have that velocity over time graph that's going to be increasing at a constant rate. And so because you're increasing your velocity each increment of time, what you're going to get is the exponentially increasing position, right? You're getting faster each time, and therefore your position is going to change exponentially. Now your acceleration is based off your velocity versus time graph, just like your velocity is based off the position over time graph, and that's represented by the slope. So the slope of the position versus time graph is your velocity. The slope of the velocity versus time graph is your acceleration. And then you want to work backwards from that, which is analyzing the area under the curve. So the area under the curve for acceleration would be change in velocity, and the area of velocity over time would represent your displacement. All right, so here's another thing you might want to take note of, which is the dot diagram. So being able to differentiate between the position of an object, whether it's speeding up or slowing down. So let's say you had like a motion camera that captured the position of an object every increment of seconds, like every 1 second. So you're able to tell whether it's speeding up or slowing down. So the first example, you can see how it's speeding up because since it's going faster, right, in that same amount of time, when it takes that picture, the distance it travels is going to be greater. And in contrast, when it slows down, that distance is going to decrease. Okay, so now we want to look at the kinematic equations, and these are the uniformly accelerated motion equations. And so you want to use these when the acceleration is constant. If acceleration isn't constant, what you can do is just break the problem apart to analyze it in parts where the acceleration is constant. So the first 3 here are on your reference table, but the 2 in green are not, and those would probably be helpful to memorize. So what you'll find is that 2 and 5 are pretty similar in terms of the content. The only difference is that the initial velocity is swapped with the final velocity. And to make up for that, instead of plus 1/2 at squared, it is minus 1/2 at squared. And another thing to know about these equations is basically if you have an unknown variable and you know the other 3 or 2 variables, then you can plug it in to solve for those. And that is sort of the basis of kinematics. And x in these examples can be interchangeable with y. It just shows the plane that is being analyzed. And you'll see it in the practice problems. Now we want to look at free fall. So this is when you just throw an object into the air and then you want to analyze its motion, or let's say you dropped a ball from a cliff. So this is where the only force acting upon that object is the force of gravity, and we're ignoring air resistance. And the acceleration due to gravity on planet Earth is negative 9.8 meters per second squared. It really is 9.8 meters per second squared, but because it's acting downwards, it's negative little g. So these are the motion graphs for it. You can see how, let's look at this first one where there is position over time. This is something that would be represented by, let's say, you throwing a ball straight up and then it comes down. So you throw it straight up and then it reaches its apex and then comes down to its initial position. And the velocity over time graph, you can see, is where you give that ball an initial velocity, but then what happens is that since the only force acting upon it is negative g, right, that acceleration is going to be, that velocity is going to be positive, but it's going to be decreasing, right, until it reaches 0, which is when it hits its apex, and then it's going to go negative and start falling back down. You can see how the areas are equal to each other. So this area right here is equivalent to this area right here, which shows the total change in displacement, which would be 0 if the ball came back down to you. And then the acceleration due to gravity is the only force acting upon it, and that's why it's just a straight line in the negatives, which shows it's being affected by that negative 9.8 meters per second squared. All right, so the other thing regarding free fall is up and down problems. And so we already talked about that symmetry that you're going to see, but there are 2 strategies you want to use when analyzing these problems. You can either analyze the whole motion, in which the displacement would be 0 because it came back down. The velocity just before landing is the negative of that initial velocity, and then the time is just the total time it took for the entire motion. Or you can just analyze just the up portion or just the down portion, in which the displacement would be max. The velocity would be 0, since when it reaches its apex, that would just stop, and then time is just half the time. All right, so the final thing we're going to cover is projectile motion in terms of kinematics. So there are 2 types of projectiles. You're going to have angled projectiles and horizontal projectiles. So when it's angled, it's launched at an angle into the air, and when it's horizontal, it's just launched at 90 degrees flat, given an initial velocity as well. And that initial velocity is going to act in the x direction. So these are a couple universal laws that would apply to these projectiles. So for the angled projectiles, what you're going to do is break that velocity into its component, right? Just like what we said before, we want to break that initial velocity right here into its different components using trig. So once we get those values, there are a couple ways to analyze it, and I'll get into that in a little bit. But now I want to look at the horizontal projectiles. So your initial acceleration in the x direction would always just be 0, right? Because after you give it the initial velocity, there's nothing acting in the x direction, since sum of all the forces in the x direction would be 0 when it's in the air. However, the acceleration in the y direction would just be the force of gravity at negative little g. And another thing to note here is that when you give it a greater velocity in the x direction, it would not affect the flight time. It only affects the displacement in the x direction. And the thing that affects time or flight time is the velocity in the y direction. And so when you get comparison questions about how long it would take and things like that, or drawing graphs, that's something you want to take note of. And another thing is that time links the x plus y directions. And so when you draw your times table like x and y, in order to see what variables you're missing, what you can do is find time using one of the either x values or y values with the uniformly accelerated motion graphs. And then you can use that to find the missing values for the other side in order to get your answer. Just a little breakdown of the different ways you can analyze it. when this angled projectile comes back down to its initial y position, like we said before with the up and down problems, the final velocity would be the same as the initial velocity but negative, times total time, and then the displacement would be 0. Now, when you want to analyze it as it goes to its max height, it reaches its apex, and so it's 0 for a moment there in terms of velocity. Time is half the time, and the displacement would be max. First topic that you sort of need to know is just to have a feel for free body diagrams, right? So you kind of have to know what all the forces are. So the force of gravity is very common and applies to pretty much every single object. So Fg, or the force of gravity, is equivalent to the mass times the gravitational constant, and it always points straight down towards the center of Earth. Now, granted, you're on Earth. There's force of friction, which is parallel to the surface and opposes motion. There's force normal, which is the force acting on the object by the surface, and it's going to be acting perpendicularly away from the center of mass of that object. And then there's tension force, or applied force. So that's basically where the force is pulling the object by a chain, rope, or anything of those means. So here's an example. Very simple. It's just a block with a mass of 2 kilograms is pulled to the right by 5 newtons of force at a constant velocity. Then you want to draw the free body diagram. So to draw the free body diagram, obviously you just draw arrows from the center of mass. It's given that it's pulled to the right by 5 newtons, so that's what we did. And because it's moving at a constant velocity, that force of friction has to be opposing it in the x direction at 5 newtons as well. We'll talk about it later in terms of Newton's second law. And then it's not accelerating in the y direction, and therefore we know that the force normal is equivalent to Fg. All right, let's move on to the Newton's first law. So Newton's first law states that an object at rest remains at rest, and if it's in motion, it will remain in motion at a constant velocity unless it's acted upon by a net external force. So in this example, you can see revisiting that block where it's 5 newtons of force of tension and then 5 newtons of force of friction, that object is either going to be at rest or moving at a constant velocity because net force is 0. And you can tell the difference between those, whether it's at rest or moving, by the type of friction. So it's either static or kinetic friction, and we will talk about that later on over here with this chart. But let's move on to Newton's second law, which is sort of like the inverse of Newton's first law, and that's where you do have a net force. So a net force will cause an acceleration in the same direction. So it's basically a equation, right? So we know that net force is equivalent to mass times acceleration. And whenever the net force increases, acceleration will also increase at a constant direct relationship. Granted, mass is constant. And then as for mass, if mass increases and the net force stays the same, then acceleration will decrease inversely. Okay, so now let's talk about Newton's third law. So basically, Newton's third law states that anytime two objects interact, they're going to experience the same force, which is equal and opposite. So the force experienced by one object on the other one is the same, except it's opposite from the other object to the original one. So here's a little example. So let's say I punched a wall with 10 newtons of force, right? So the force of the wall on my hand is also going to be 10 newtons, except it's going to be acting towards my hand. And so it's going to be acting in the left, right? And we define the left as negative, and that's why it's equal and opposite. All right, so let's now talk about friction. So the first thing I want to touch upon is static versus kinetic friction. So we have this chart here, which shows that over time, as force is applied, the static friction is the first one which pops up, and that is where friction hits a max, right? Because that's the amount of force that it takes to get something moving against friction. But once you do get it moving, now you're going to have kinetic friction, which is the friction that opposes the object when it's moving. So static friction will always be greater than kinetic friction because it takes more force to get something moving than to continuously have it move after the initial force. So another thing to note is that force of friction is equivalent to mu, which is the coefficient of static friction, but the equation is interchangeable with kinetic friction, and the problem will usually tell you which one it is, times force normal. So the coefficient is a property, so it tells us how rough the surface is. It ranges from 0 to 1, with 0 being frictionless, and you can only change it by changing the surface. Another thing to note here is that if the object is not accelerating in the y direction, then Fn is equivalent to Fg, and so that means that if you have greater mass, there's going to be more force of friction. All right, so components of vectors. So this is where we talked about this in like kinematics, the kinematics review. So after this video, if you haven't seen the kinematics review, I would highly recommend you check that out as well. So this is where, let's say you had a sled, right, and you pulled it at an angle. That force of tension is not going to like act equally. And so in order to observe the effects of the force, you have to break it apart into its components and observe it in the x and y direction. So you can see here, in order to do that, you would have to know theta, the angle that's pulled at, or the angle that the force makes with the horizontal. And then you can just use trig in order to find each of those values. And I have a little example here showing the net force, right? So the net force in the x direction is just that component of Ft in the x direction plus the force of friction. And the force of friction is negative. That's why it's negative Ff. And in the y direction, it's force normal, acting in the positive because it's going up. And then that force of tension y plus Fg. And Fg is negative because it's acting downwards, which we define as negative. All right, I think the next thing I want to go to is actually elevator problems. So the elevator problems are a pretty simple topic, but basically what you need to know is that when you step on a scale, it's reading the normal force. So what this means is when you step on a scale, let's say on Earth versus on the moon, that's going to be different, right? Your mass is different from your weight. So because of this, let's say you're on an elevator and it's accelerating in a certain direction, then that means according to Newton's second law, there must be an imbalanced force. And so the force in the direction of the acceleration must be greater because there's an imbalanced force, right, to cause that acceleration. So let's say I have this guy here in this elevator, and the elevator is accelerating upwards. So this means that the imbalanced force here would have to be Fn. So Fn has to be greater than Fg. And when I put it into the equation, the net force acting in the y would be Fn as the positive, and then plus negative Fg. And then I would set this equal to m mass times acceleration, and then you'll find that Fn will indeed be greater than Fg. All right, so the next thing I want to do before we talk about forces on an incline is systems. So there's no like specific thing for systems, but these are just a couple key takeaways I would definitely note about systems, because this is a pretty big topic and the majority of forces problems are probably going to be observed through a systems lens. So it has to deal with interactions between multiple objects, right? And for AP Physics 1, strings and pulleys are massless. And a couple key pointers is you want to observe systems as one object accelerating. So you can sort of like take away the internal forces and then just observe the outside forces to see what's affecting the system, and then zoom in on that one object. You want to label the forces that are trying to accelerate versus trying to stop the system from accelerating. So that's that, looking at it from lens of the system. And you also want to use sum of the forces equals ma for the system, because in most cases when the entire system is moving as a unit, the acceleration in the system is equivalent to the acceleration for an object in the system. So once you find the acceleration in the system, you can then use net force equals ma, so Newton's second law, to find the sum of the forces, and then sum of the forces for like the object, and then you can just plug it in for sum of the forces of the object equals the mass of the object times acceleration, in order to find string tensions, other forces acting on the object, etc. So here's a little practice problem. So we have the system here of two blocks, and they're connected by a string. So it's accelerating downwards because of that 5 kilogram mass, and then that 2 kilogram mass is just on the table. And so when we observe it from a system's perspective, the net force on it is just the force of gravity acting upon that 5 kilogram mass. So the force of gravity would just be 5 mg, right? Mg. So 5 times 9.8 equals 49 newtons. Internal forces of force of tension cancel out, and then the mass of the system would be the total mass. So we have the 2 kilogram and the 5 kilogram. And so we can calculate that the acceleration is 7 meters per second squared. And since it's moving as a unit, that's the acceleration of the system and the objects inside. And so now we can just calculate the force of tension by looking at the first object. So the first object, sum of all the forces, is that force of tension, because the force of tension is the only one acting upon it in that direction. There's the force of gravity and force of normal force, but those are equal because it's not accelerating up and down, that is. So sum of the forces equals ma. So the mass of the object is 2 kilograms because we're only looking at it from the lens of observing one object. And then the acceleration, we already know, of the system is 7 meters per second. So for the object, it must also be 7 meters per second squared. 2 times 7 is 14 newtons. And since we know that the only force acting in the x direction is a force of tension, that force of tension must equal 14 newtons. Now, let's look at forces on an incline. So whenever you have like a block on an incline or just any object, you can break force of gravity into its components where you have to, because very similar to where that force of tension was acting on like the sled problems, it acts on x and y differently. So we call those directions FG perpendicular for the y and FG parallel for the x. I'm going to use trig to find the magnitudes, and here's a little proof to see which angle in that right triangle you create is actually theta. So just a couple things to note for the block when it's in like equilibrium is that the sum of all the forces in the x is 0, sum of all the forces in the y is 0, and therefore the forces acting in those directions are supposed to be equal to each other. So force of friction, that's static, is going to be equal to the FG parallel component, as you can see up here, where the forces are acting in the direction. So FG is acting in the x, FG perpendicular is acting in the x, Fn is acting in the y, and FG perpendicular is acting in the y. So here's a problem solving tip. Mu, the coefficient of static friction or kinetic friction, sort of links the x and y directions. So force of friction over Fn equals mu. So if you know two of the variables, you can just solve for the last one. Force of friction, we know acts in the x, and force normal acts in the y. And so that's sort of that link whenever you have a problem that's asking for one of those variables. And here's another thing where force of friction kinetic, if it does note that, means that the object is moving at a constant velocity, right? And here's another thing for when the object is not at equilibrium, so when it's accelerating. So here, the problems can vary. So these are just very general guidelines you want to follow, and you want to adjust it based on the problem. So usually net force in the y will be 0 because it's not going through the block, right? And when it does accelerate, that usually means there's a net force in the x direction. And so usually what that means is if there's not a rope or tension or something, then FG parallel will be greater than force of friction, which is causing that net force and therefore causing acceleration. So Hooke's law states that the force on the spring is equivalent to the spring constant, which is a constant force, and it's just a measure of how strong the spring is, times the change in length from the equilibrium position. So that is when it's not stretched. Something to note here is that when it's oscillating, if it's the restoring force, it's going to be negative kx instead of just kx. Because if you think about it, I should draw this out. So if you have, let's say this, and then you have the spring here, and there's a ball attached to the end. So once it reaches its maximum displacement, there needs to be a force which acts in the negative direction here to get that ball to go back and oscillate.
So essentially, whenever you have objects that are moving in a circle, in order for that to happen, you're going to have what is called a centripetal force. So they're going to have a change in direction. They're constantly changing direction, and therefore their velocity is always going to be changing, and that requires a force, right? But just because their velocity is changing doesn't mean that the magnitude of the velocity, which is speed, changes as well. So the speed does not change and instead stays constant. So what is a centripetal force? So a centripetal force is going to be a net force, right? Because it's derived essentially from Newton's second law. A net force will cause an acceleration. So the centripetal force is the net force that is responsible for keeping an object in a circle. So whenever you have net force, there must be an acceleration, right? So here is an example of that. We have a ball in uniform circular motion, and basically what you're doing is you're just swinging it on a string vertically, right? And then when it's at this moment, we've captured it. The net force on it is going to be Fg, the force of gravity pointing straight down towards Earth, and then the force of tension also pointing straight down because the ball is at its apex right now. So we define the center of the circle as positive and away from the center or outside of the circle as negative. So in this case, the net force would be Fg plus Ft. And what you'll find is that your net force will always be the greater value because that is the direction in which the acceleration will point. Another thing to note here is that when you're writing out the centripetal force, it is expressed as AC, or rather V squared over R, all right? So that is the important thing to note there about notation-wise of equations. And here are a couple guidelines when drawing those diagrams. So for free body diagrams, you're not going to have any new forces. However, there are some slight adjustments and caveats you want to take into consideration. So the net force, like we talked about, will always point towards the center of the circle. The velocity is tangent to the circle. The acceleration is just how quickly the velocity changes. That's AC. There's no force. If it asks you to draw a free body diagram, you're not going to be drawing the velocity or the acceleration on there, obviously, and the speed stays the same. So there is this thing called critical velocity. So critical velocity is basically the minimum or maximum velocity you need to either make it through a loop or to go over a hill or stay on a surface. Essentially, this is where you're going to be setting the normal force to 0, and then solving for velocity there. So usually it's going to involve some sort of contact, like a car on a hill or a car on a surface or something. So that's just something to know about critical velocity.
Types of energy. So the first energy that we have is gravitational potential energy, right? So gravitational potential energy is going to be independent of motion, and it's also based on the object's position in the gravitational field. So what exactly does that mean? Well, the important thing here is to identify the what we call the horizontal zero line. So if I have this guy on a cliff, right, and I use mgh, which is the equation for gravitational potential energy, I can call that base of the cliff, the ground, y equals 0. So when I do my calculation, mgh, that height is just going to be the height of the cliff. But let's say I'm on an airplane, right? That height, if I was to identify the horizontal zero line as the ground, then that height would be thousands of feet, right? However, if I identify the horizontal zero line as y equals 0 in respect to all motion, then that height is going to be much, much lower. And so my gravitational potential energy is going to be much lower as well. So the next type of energy is kinetic energy. So kinetic energy is just the energy of motion. And you can see this through translational or linear kinetic energy or rotational kinetic energy. And the final one is spring potential energy. So that's just potential energy that is stored in a spring. And there are other ones like electrical energy, but those aren't really relevant for calculations in this course. All right, so now let's talk about conservation of energy. When there's no external forces acting upon objects in a system, that is where energy is conserved. So energy initial equals energy final. All right, so here's an equation that represents that. And this is where there's non-conservative forces that aren't acting upon it, right? So we're going to have something like air resistance or friction, which is going to be represented as work other. So kinetic initial plus U, which is potential energy initial, plus work equals kinetic final plus potential energy final. And something important to point out here is that it could just start off with all gravitational potential energy if it's, say, like a ball released from a cliff or something from rest. So that can always change, but the point here is that energy can't be created and will always take other types of forms, and that is where you have to represent them using these equations. All right, so now let's talk about the concept of work. So work is just change in energy. It has the units of joules or Newton meters, and it's equivalent to the force parallel times displacement. And the displacement can both be either vertical or horizontal. So something to know about work is that work can both be positive or negative depending on the directions of the force and displacement. So what I mean by parallel is that if the force is parallel to the displacement and they are in the same direction, then it'll be positive work. Now, if the force is parallel, but in the opposite direction of that displacement, then it's going to be negative work because it's going to be acting against it. All right, and the graph of force times displacement is equivalent to work. And that can be easily seen through that equation where the values are multiplied. Okay, so now let's talk about work at an angle, because when you have work, say you have a box or something and you're pulling it with a rope or a string or something, that work is not going to be evenly distributed. So that entire force is going to be acting in components, and that's a big part of physics where you have to observe things from a component perspective. But now the equation changes slightly. So now instead of work equals force parallel times displacement, you're going to have work equals force times displacement times cosine theta. All right. So here is a pretty nice chart which lays everything out. So when that cosine theta, when theta is in between 0 and 90 degrees, you're going to get a positive value for cosine theta. And that also means you're going to have positive work, which means the speed of the object is going to be increasing, right? Because work is change in energy. So if your change in energy is increasing, that means you have more kinetic energy. When theta is 90 degrees, that means cosine theta is 0, which means you're going to have 0 work. And so the speed of the object is constant. So when theta is in between 90 and 180 degrees, you're going to get a negative value for cosine theta, and therefore you're going to get negative work. And so that means a decrease in the amount of energy, which means the decrease in speed as well now. All right, so the final thing we want to touch upon is springs, and then I'll get to power. So for springs, there's two things you want to know, and that is Hooke's law and the spring potential energy equation. So Hooke's law states that the force on the spring is equivalent to the spring constant, which is a constant force, and it's just a measure of how strong the spring is, times the change in length from the equilibrium position. So that is when it's not stretched. Something to note here is that when it's oscillating in simple harmonic motion or something, if it's the restoring force, it's going to be negative kx instead of just kx. Because if you think about it, I should draw this out. So if you have, let's say this, and then you have the spring here, and there's a ball attached to the end. So once it reaches its maximum displacement, there needs to be a force which acts in the negative direction here to get that ball to go back and oscillate and go through its equilibrium position again. So if we observe that chart or the graph of force over change in length from the equilibrium position, that is going to be equivalent to K, the spring constant, which is the slope. But like we talked about before, the area of force over displacement is work. And in this case, we have force over displacement from the equilibrium position. And so we know that the area of this graph is also the change in energy, right? And so when you find this change in energy, a lot of times what you'll do is then plug that in for spring potential energy. So when you work with Hooke's law, think springs, think spring potential energy. So that's something just to keep in mind. So the final thing here is power. So power is just how quickly does work happen. And power is represented by the change in energy over change in time. And that one equation will probably serve you well, but there is another way of thinking about it. So since change in energy, we know on the reference table, it's given as force times displacement, right? So if in our power equation, we just substitute change in energy for force times displacement. Now we have power equals force times displacement over time. Now we know that d over t, or displacement over time, is just the velocity, right? That is just force times velocity, right? Because d over t is the velocity. And so power is also equivalent to force times velocity.
So momentum, it is a vector. It's denoted by the symbol p, and it's equivalent to mass times velocity, and its units are kilograms times meters per second. So a mass of motion will have momentum, and you can think of momentum as how hard it is to stop something, all right? So the first big idea of momentum is conservation of momentum. So in closed systems without external forces, momentum is always conserved. And we think about this again in terms of collisions. So here's the general equation for conservation of momentum. So it's just sum of the momentum initial is equivalent to sum of the momentum final. Very similar to conservation of energy, actually. So you can see here that if we have two objects, let's say A and B, and they're involved in a collision, we can set it up where we break down each of the objects into their individual momentums. So for momentum of A, for example, initial, we can break it up into mass of A times velocity of A initial. Plus, for B, we have the momentum of B as mass of B times velocity of B initial. And this gives us our corresponding final values, as you can see there. Now, sometimes momentum is not always conserved in both directions. So you want to break up momentum into its components, like we've seen in the other units, right? So just because momentum might be conserved in the x direction doesn't necessarily mean it's conserved in the y direction. So that's just something to be careful of. All right, so here's a little bit about center of mass. So if there are no external forces, the motion of the center of mass will not change. And this relates to the second point where the forces that are interacting within the system will stay internal to the system. So those forces inside the system are not going to affect the motion of center of mass or say the velocity of the center of mass from its initial position. So the second big idea is impulse. So impulse is what changes the momentum of the object, and it's denoted by the symbol newtons times seconds. So impulse is a vector value, and basically you can derive it from Newton's second law. We can see here that acceleration can also be expressed as change in velocity over change in time, and therefore we can just multiply time on both sides to get ft equals m times change in v. So m times change in v is also just change in momentum. So change in momentum is equal to ft, which is equivalent to impulse. And so here you can see on our motion graph here, or rather just impulse graph, it's force times time. So you can see that the area under the curve represents the impulse, which is change of momentum, which is just final momentum minus initial momentum. And now we want to talk about collisions. So collisions are built on the foundation of Newton's third law. So there's a mutual force that each block is going to be experiencing when they collide, right? So the first type of collision are elastic collisions. So elastic collisions sort of bounce in opposite directions. And elastic collisions will conserve both kinetic energy and momentum. So here's an example. You have mass 1 coming towards, cart 1 coming towards cart 2 of m2. And cart 1 has a velocity of v1. Cart 2 has a velocity of v2. And we can see that they're set equal to each other. And so their total momentum initially will be 0. And so if we were to set up the total momentum equation of initial momentum equals final momentum, this is what it might look like. We can see that we're just breaking it up. M1 times V1, that represents the initial momentum of cart 1. And then everything final, as you can see here, mass 1, VF1, etc., etc. Now the second type of collision we have is inelastic. So inelastic collisions where momentum is still conserved, but now the kinetic energy is lost.
So let's say we have two masses coming towards each other. We're going to have what is either perfectly inelastic, so they're going to stick together, and this results in the largest loss of kinetic energy. And so when we set up our conservation of momentum equation, we have m1 times v1 plus m2 times v2 is equivalent to m1 plus m2, and then the entire thing times v, and v is representing the final velocity in which both blocks have because they're moving as one object, as one unit in the system. Now they can also just be elastic, so they're just going to generally travel in the same direction. And then the equation is pretty similar to the elastic equation, except now taking into account those vector directions. That is really what makes the difference in these momentum equations. So whenever you have a loss of kinetic energy and you're asked to calculate it, all you have to do is use kinetic energy equals 1/2 mv squared. You can see as the variables of mass and velocity, which usually you will be able to solve if you're doing momentum equations. So you can use this to find the loss of energy. And now just some final things, quick tips for momentum problems. Make sure you draw your diagrams and list the givens always for any type of problem. Identify whether there's impulse or conservation of momentum. It'll help you get started with problem solving. And then you also want to account for velocity, vectors, and directions. That's super important, especially for collisions. I mean, it can absolutely make the difference.